Today we're going to be solving multiple choice questions for AS energetics. We're going to start with this question, which says nitric oxide and bromine vapor react together according to the following equation. The reaction has an activation energy of positive 5.4 kilojoules per mole. What is the correct reaction pathway diagram for this reaction? So obviously the activation energy is positive. It's always going to be positive, whereas the enthalpy change is negative, right? It's an exothermic reaction. Right, so which diagram shows the correct pathway diagram? Again, the enthalpy change is exothermic, right? So that means we have a downward arrow. We have a downward arrow from reactants to products, right? So it could be A or D, right? Obviously, this is not the enthalpy change because this is not showing the arrow from reactants, right? The arrow should be from reactants to products like this, right? Reactants to products. So it has to be A or D. So which of them shows the activation energy correctly? Diagram D shows the correct activation energy, right? The enthalpy change is shown correctly from reactants to products, right? From reactants to products. And the activation energy should be shown from the reactants to the highest energy point, right? So the answer here will be D, right? This is the correct reaction profile for this reaction. Okay. The next question that we have is gaseous phosphorus pentachloride can be decomposed into gaseous phosphorus trichloride and chlorine by heating. The table gives the bond energies. What is the enthalpy change for the decomposition of PCl5 to PCl3 and Cl2? Now they've given us the bond energies, right? They've given us the bond energies of the PCl bond and the Cl-Cl bond, right? So again, we're talking about this reaction. We have PCl5 making PCl3 and Cl2. So we know that the enthalpy change of a reaction, right? The enthalpy change of a reaction in terms of bond energies, right, is the bond energies of the bonds broken, right, minus the bond energies of the bonds formed, right? Minus the bond energies of the bonds formed. Okay, or we can say the bond energy of the reactants minus the bond energies of the products, right? Now, we have PCl5. So we have in PCl5 we have five PCl bonds, right? We have 5 PCl bonds, right? And what we're doing here is we're breaking 2 of these PCl bonds. We're breaking 2 of these PCl bonds, right? So we're forming PCl3. So the bonds broken here are for 1 mole of PCl5, we're going to break 2 moles of PCl bonds. So the bonds broken would be 2 times or twice the bond energy of PCl. That's 2 times 330, right? And then we're forming 1 mole of Cl-Cl bonds, right? We're forming a Cl-Cl bond when we form chlorine, right? So that would be, we're going to subtract the bond energy of the bond that we're forming. So we're bonding 1 mole of Cl-Cl bond, so that'll be minus 242, which gives us an enthalpy change of, so we get a value of positive 418 kilojoules per mole for the enthalpy change, okay? So the answer over here is D. Right now, obviously, alternatively, you could say we're breaking all 5 PCl bonds and then we're making 3 PCl bonds, right? The overall change would just be the fact that we're breaking 2 PCl bonds. So you could do bond energy of reactants minus products, or you could just say, you could just identify the bonds being broken and the bonds being formed, okay? And you could just subtract the bond energy of the bonds formed from the bond energy of the bonds broken, okay? The next part says, or the next question says, the equation for the complete combustion of propan-1-ol is shown. The standard enthalpy changes of formation are given. What is the standard enthalpy change of combustion of propan-1-ol in kilojoules per mole? And in this equation that is shown, what is the enthalpy change for this reaction, right? The enthalpy change for this reaction is the enthalpy change of combustion of, propan-1-ol, right? Since we have 1 mole of propan-1-ol being completely combusted in excess oxygen to form products in their standard states. Now we want to find the enthalpy change of this reaction, right? That's the standard enthalpy change of combustion of propan-1-ol. And we know that the enthalpy change of a reaction, right? If we're given enthalpy change of formation data, right? Like we are here, we're given enthalpy change of formation data. We know that the enthalpy change of a reaction is simply the enthalpy change of formation of products, right? Enthalpy change of formation of products, or the sum of the enthalpy change of formation of products minus the sum of the enthalpy change of formation of reactants, right? Again, This applies if we've been given enthalpy change of formation data. We can use this expression to calculate the enthalpy change of a reaction. Right now over here, if we look at our products, we have 3 moles of carbon dioxide and 4 moles of H2O. Right, so the enthalpy change of formation of products will be 3 times the number of moles of carbon dioxide. So that's 3 times negative 394. Right. Then we have 4 moles of H2O in the product. So we're going to add the enthalpy change of formation of that. So we have 4 times negative 286. And then we're going to subtract the enthalpy change of formation of all the reactants. Now here we just have the enthalpy change of formation of propane 1-ol, right, which is negative 303. So that'll be minus 303. Okay, we're going to subtract the enthalpy change of formation of the reactants. And obviously the enthalpy change of formation of oxygen gas is just an element in a standard state, so that'll be 0. So over here we get 3 times negative 394 plus 4 times negative 286 plus 303, right? So we get 3 times negative 394 plus 4 times negative 286 plus 303, right? Because minus is plus, right? So then the answer over here is B, right? 303 minus 4 times 286 and minus 3 times 394. So the answer is B. All right. Enthalpy changes can be positive or negative. The question says which row is correct. So when we talk about enthalpy change being positive, we know that bond breaking, okay, bond breaking and atomization are positive. Again, atomization is no longer in our syllabus, okay, but we know that bond breaking is endothermic, whereas bond making is exothermic, and combustion is also exothermic, right? So it can't be C or D. As far as delta H negative is concerned, we know that bond breaking again is positive, right? It's endothermic, so it can't be this, whereas neutralization is always exothermic. Okay, so the answer here is B, right? Bond breaking is endothermic and neutralization is exothermic. Methanol may be prepared by the reaction between carbon monoxide and hydrogen. The relevant average bond energies are given. What is the enthalpy change of this reaction? So again, over here, we know that the enthalpy change of the reaction, right, in terms of bond energies, is the bond energy of the bonds broken minus the bonds formed, right? That is just the bond energies of the reactants minus the bond energies of the products. So over here, if we look at the reactants, we have carbon monoxide, right, where we have C triple bond O. So that'll be 1077, right? We have 1 mole of carbon monoxide, so we have 1 mole of triple bonds, right? We have 1 mole of triple bonds because every molecule of carbon monoxide just has 1 triple bond. Right? We have 2 moles of hydrogen gas. Now, every molecule of hydrogen has 1 single bond. So if we have 2 moles of molecules, that means we have 2 moles of HH single bonds, right? So we can say this will be plus 2 times 436, right? Because we have 2 moles of the HH bond. And then we're going to subtract the bond energies of the products, right? Now in this case, we have CH3OH, right? We have 1 mole of methanol, right? Now in 1 mole of methanol, we have 3 moles of CH bonds. Okay, we have 3 moles of CH bonds. So we have 3 times 410. Okay. We have 1 mole of C single bond O, right? So that'll be minus 360, right? And then we have 1 mole of O single bond H. Okay, so that'll be minus 460. We're going to subtract the bond energies of the products or the bonds that are forming. So we get the enthalpy change of the reaction as, we get it to be negative 101 kilojoules per mole. Okay, so the answer here is B. An important reaction in the manufacture of nitric acid is the catalytic oxidation of ammonia. For every mole of oxygen that reacts in this way, 181.8 kilojoules of energy are released. A factory makes 2.5 into 10 to the power of 5 moles of nitrogen monoxide every day. How much energy in kilojoules is released every day? So over here, they've told us the amount of energy that's released, for every mole of oxygen. So if 1 mole of oxygen reacted, this much energy would be released, right? And they've told us how much nitrogen monoxide is being made. So we can just figure out the number of moles of oxygen, right? We know that for the molar ratio between oxygen and nitrogen monoxide is that for every 5 moles of oxygen, we get 4 moles of nitrogen monoxide, right? For every 5 moles of oxygen, we get 4 moles of nitrogen monoxide. So if we have 2.5 into 10 to the power of 5 moles of nitrogen monoxide, how many moles of oxygen do we have? So the number of moles of oxygen is equal to, this is equal to 3.125 into 10 to the power of 5 moles. Okay, so this is the number of moles of oxygen that we have, right? Now for every 1 mole, 181.8 kilojoules are released, right? So 1 mole of oxygen being reacted releases 181.8 kilojoules of energy, right? So if we had 3.125 into 10 to the power of 5 moles of oxygen, how much energy would be released? So over here, we can say that the energy that is being released every single day is 3.125 into 10 to the power of 5 multiplied by 181.8. So over here we get the answer as 5.68 into 10 to the power of 7 kilojoules. Okay. Again, over here we just cross multiplied, right? We multiply this by this to get the energy. So the answer is C. At 550 degrees Celsius, nitrogen dioxide reacts with unburnt hydrocarbon fragments, such as a methyl group. This is a methyl radical, okay, in the catalytic converter of a motor vehicle. The following table lists types of energy change for this reaction and possible reasons for them. Which row gives the energy change for this reaction and the reason for it? Over here, we don't know if the reaction is actually endothermic or exothermic, okay? But we have to deduce whether it's endothermic or exothermic based on the reason that's given to us, okay? Now, if we look at option A, right, it says that the reaction is endothermic because the chemical energy is converted to heat energy. That's incorrect, okay? Because heat energy is released in exothermic reactions, right? So this is incorrect. For endothermic reactions, heat energy is converted into chemical energy, right? So A is incorrect, right? If you look at option B, right, it says that the reaction is endothermic because the nitrogen-nitrogen triple bond energy is very high. In other words, the triple bond is very strong. But again, we're not really breaking any nitrogen-nitrogen triple bond, right? Here, the nitrogen-nitrogen triple bond is forming, right? The NN triple bond is forming, right? So if the bond energy was very high, it would actually explain why the reaction is exothermic, because the bond is forming, right? So again, this is not a valid reason as to why the reaction would be endothermic, right? Because there's no nitrogen reacting. The third reason given to us is that the reaction is exothermic, and it says that the carbon dioxide and H2O have large negative enthalpy change of formation values. Now, the enthalpy change of a reaction in terms of enthalpy changes of formation is the enthalpy change of formation of products minus the enthalpy change of formation of reactants, right? Now, the more exothermic the enthalpy change of formation of products, okay? The more exothermic the enthalpy change of formation of products, okay? The more exothermic the enthalpy change of the reaction, okay? The more exothermic the enthalpy change of formation of products, the more negative this value is, the more negative the overall enthalpy change will be. Okay, so if the enthalpy change of formation of products is highly exothermic, it means that the formation of products is highly favorable, which would mean that the reaction overall is exothermic. And here carbon dioxide and H2O are products, right? So if they have large exothermic enthalpy change of formation values, it would mean that the enthalpy change of the reaction is also exothermic, okay? And we can also eliminate option D, which says that the reaction is exothermic because double bonds are broken in NO2. Now, if the double bonds are broken in NO2, right, there would be strong double bonds, right? There would be strong double bonds, and a lot of energy would be needed for that, right? A lot of energy would be needed for that. So again, this would actually explain why the reaction would be endothermic if it was indeed endothermic. So here, obviously, this is not a valid reason for the reaction being exothermic. So it can't be option D either. All right, the next question that we have says the diagram shows the pathways of a reaction with and without a catalyst. Which letter represents the overall energy change for the reaction? The overall enthalpy change of the reaction would be the enthalpy change when the products are formed from the reactants, right? So that would be the arrow from the reactants to the products, right? So that the magnitude of that is just C, right? So the letter C represents the enthalpy change of the reaction. Okay. In a calorimetric experiment, 1.6 grams of fuel are burnt. 45% of the energy released is absorbed by 200 grams of water. The temperature of the water rises from 18 degrees Celsius to 66 degrees Celsius. What is the total energy released per gram of fuel burnt? So the first thing we would do here is actually figure out how much of the energy was absorbed by the water, right? The heat energy absorbed by the water, right? So we can say the heat energy absorbed by the water, that's Q, is equal to mc delta T, right? Where m is the mass of water, C is the specific heat capacity of water, and delta T is the change in temperature. Now the mass of water that we're using is 200 grams, right? So we have 200. The specific heat capacity of water is 4.18 joules per gram per Kelvin. And the change in temperature is, we go from 18 degrees Celsius to 66 degrees Celsius, so 66 minus 18, which is 48 degrees Celsius, right? Or 48 Kelvin. So here we get Q as, so over here, okay, we get the energy or the heat energy that was absorbed by the water as 40,128 joules. Now, of course, this is not the total amount of energy that was released, right? The question tells us that 45% of the energy released was absorbed by the water, right? So we figured out how much energy was absorbed by the water, right? This is the energy. This is the energy absorbed by the water, right? And we know that this is 45% of the total amount of energy. So let's say that the total amount of energy is E subscript T, right? Let's say this is the total amount of energy. And we know that 45% of the total amount of energy, that's 45 over 100, right? 45% of the total amount of energy is the amount of energy that was absorbed, right? That's 40,128. So what was the total amount of energy that was released? So the total amount of energy that was released is 89173 joules. Now we want to know what is the total energy released per gram of fuel burnt. This is the total amount of energy that was released. Okay, this is the total amount of energy that was released when 1.6 grams of fuel were burnt, right? 1.6 grams of fuel released 89,173 joules. So per gram of fuel, if we had 1 gram of fuel, what would be the energy released? Right, if we want to find the energy released per gram, we're going to divide the total energy by the mass of the fuel in grams. So we have 89173 divided by 1.6, which is equal to 55,700 joules, right? To 3 significant figures. So the answer over here is B. All right. All the reactants and products of an exothermic reaction are gaseous. Which statement about this reaction is correct? Now, for an exothermic reaction, right, we know that the bond energy of the products is more than the bond energy of the reactants, right? For an exothermic reaction, more energy is released when the bonds form, right? If we had reactants here and we had products here, right, we know that more energy is released when bonds form than the energy that was needed to break the bonds in the reactant. So the bond energies of the products are greater. Okay, the products are more stable, they're at a lower energy, and therefore they have stronger bonds, right? Or they have stronger bonds and therefore they're at a lower energy, right? That's why they're more stable. So the bond energy of the products is more than the bond energy of the reactants, and the delta H for the reaction is negative, right? So this describes an exothermic reaction, okay? Which expression gives the standard enthalpy change of combustion of methane in terms of enthalpy change of formation data? Now, if we had to find the standard enthalpy change of combustion of methane, right, we have 1 mole of methane reacting with oxygen to form carbon dioxide and water, right? And if we balance this equation, we're going to have 2H2O, we're going to have 2O2. Now, again, we want to find the enthalpy change of this reaction, right? This is the enthalpy change of combustion, the standard enthalpy change of combustion of methane, okay? And we've been given formation data, right? So if we were given the enthalpy change of formation of methane, carbon dioxide, and H2O, obviously the enthalpy change of formation of oxygen is 0. And we know that the enthalpy change of the reaction, right? The enthalpy change of the reaction is equal to the sum of the enthalpy changes of formation of products minus the enthalpy changes of formation of the reactants, right? So over here, if we look at the products, we have 1 mole of carbon dioxide and 2 moles of H2O, right? So we have the enthalpy change of formation of carbon dioxide plus 2 times the enthalpy change of formation of H2O, right? The enthalpy change of formation of carbon dioxide plus 2 times the enthalpy change of formation of H2O, right? And then we're going to subtract the enthalpy change of formation of methane, right? So this is the enthalpy change of formation of the products, right? And we're going to subtract the enthalpy change of formation of the reactants, right? In this case, the reactant, we have 1 mole of methane, right? So the answer over here is D. Okay, the answer over here is D. All right. In the high temperatures of car engines, nitrogen reacts with oxygen to give nitrogen monoxide. This reaction has activation energy EA. Which reaction pathway diagram could correctly represent this reaction? So over here, the delta H, the enthalpy change is positive. So we have an endothermic reaction, right? So the product should be higher in energy than the reactants, right? So it can't be option A, right? And option B, the enthalpy change is shown correctly, but the activation energy is shown incorrectly, right? The enthalpy change is positive from reactants to products. It's an upward arrow, but the activation energy should be from reactants to the top, right? To the highest energy point. So it can't be A or B, right? If we look at option C, right, the activation energy is shown correctly from reactants to the highest energy point, and the enthalpy change is also shown correctly, right? It's an endothermic reaction. So the answer is C. Okay, the answer is C. And again, in D, the activation energy is shown incorrectly, right, with the downward arrow. The activation energy should be shown with the upward arrow. The following data are needed for this question. What is the enthalpy change when 55.8 grams of iron are produced by this reaction? Now over here, right, if we're making 55.8 grams of iron, right, that is just 1 mole of iron, right? That's the molar mass of iron. So we're making 1 mole of iron by this in this reaction. Okay, if we calculate the enthalpy change of the reaction that they've shown us, you know, the enthalpy change of a reaction is again the enthalpy change of formation of products, okay, minus the enthalpy change of formation of reactants, right? Now the products over here, we have 3 moles of carbon dioxide. So that's 3 times negative 394. Okay. We have 2 moles of iron, right? The enthalpy change of formation of iron is just an element in its standard state. So that'll be 0, right? And then we're going to subtract the enthalpy change of formation of the reactants. Again, the enthalpy change of formation of iron, which is an element, is just 0. So that's the products, and we subtract the enthalpy change of formation of the reactants. We have 1 mole of Fe2O3, that's minus 822. So we subtract that, and we subtract the enthalpy change of formation of carbon monoxide. And we have 3 moles of carbon monoxide. That'll be minus 3 times negative 111. Okay, and this gives us the enthalpy change as negative 27 kilojoules per mole. Okay, now this is the enthalpy change. This is the enthalpy change for the reaction as they've shown us, right? And again, for enthalpy changes, the coefficients, the stoichiometric coefficients, right? The coefficients of the substances in the equation represent the actual number of moles. So this is the enthalpy change. Negative 27 kilojoules is the enthalpy change if 2 moles of iron were produced. The question is asking what is the enthalpy change if 1 mole of iron was produced? Okay, so we're going to divide this by 2. Okay, so we can say that the enthalpy change of the reaction for 1 mole of iron being produced, okay, the enthalpy change per mole of iron, okay, is going to be negative 27 divided by 2, which is negative 13.5 kilojoules. Okay, so the answer over here is B. Again, in this question, they told us what is the enthalpy change when 55.8 grams of iron are produced, right? 55.8 grams of iron, that's just the molar mass of iron. Okay, so that means what's the enthalpy change when 1 mole of iron is produced? Now, the calculation that we've done, right, for the equation that we've calculated the enthalpy change for, that enthalpy change is for 2 moles of iron being produced. So if 1 mole was being produced, then the enthalpy change would have been half of this. Okay, this is the enthalpy change if 2 moles of iron were produced, and half of that would be the enthalpy change when 1 mole of iron was produced. So sulfur can be oxidized in 2 ways. Okay, we can make sulfur dioxide from sulfur, or we can make sulfur trioxide from sulfur, right, by reacting it with oxygen. Sulfur trioxide can also be made from sulfur dioxide and oxygen. What is the standard enthalpy change for this reaction? Now over here, if we notice, right, they've given us the formation of sulfur dioxide from its constituent elements, right? So this is the enthalpy change of formation. This is the enthalpy change of formation of sulfur dioxide, right? And they've given us the formation of sulfur trioxide from its elements. But here we're forming 2 moles of sulfur trioxide, right? Again, enthalpy change of formation is for 1 mole of sulfur trioxide. So this is 2 times the enthalpy change of formation of sulfur trioxide, right? We have to find the enthalpy change of this reaction, right? And the enthalpy change for this reaction will be the enthalpy change of formation of sulfur, 2 times the enthalpy change of formation of sulfur trioxide, right? That is again the enthalpy change of formation of products minus the enthalpy change of formation of reactants. Here again, we have 2 moles of sulfur dioxide in the reaction. So we have 2 times the enthalpy change of formation of sulfur dioxide. Now this value here is 2 times the enthalpy change of formation of sulfur trioxide, right? Since we have 2 moles of sulfur trioxide here. So this value is just negative 791.4. That's 2 times the enthalpy change of formation of sulfur trioxide. And we subtract 2 times the enthalpy change of formation of sulfur dioxide. The enthalpy change of formation of sulfur dioxide is negative 296.5. So over here, okay, the answer comes out to negative 198.4 kilojoules per mole. Okay, so the answer is D. Okay. The enthalpy change of reaction 1 is negative 114 kilojoules per mole. By using this information, what is the most likely value for the enthalpy change of reaction 2? Now in both reactions, okay, we have neutralization taking place, right? The enthalpy change for this reaction is going to be 2 times the enthalpy change of neutralization, because we're forming 2 moles of water, right, when an acid is being neutralized by an alkali. And the same thing is happening in the other case. 2 moles of H plus are being neutralized by 2 moles of OH minus to form 2 moles of H2O. So the enthalpy change is 2 times the enthalpy change of neutralization. So in both reactions, we have 2H plus reacting with 2OH minus to give us 2H2O, right? Those are the ionic equations for both reactions, right? Which means that both reactions will have the same enthalpy change. Okay, we have the same number of moles of water being formed due to neutralization. So both reactions will have the exact same enthalpy change. Here you should be able to identify that we have metal hydroxides reacting with strong acids to form salt and water, right? So all the ions, the sodium ions, the barium ions, the sulfate ions, the chloride ions, they're all spectator ions, right? The reaction that's taking place here is neutralization between H plus and OH minus to form H2O. And since we're making 2 moles of H2O in both cases, we have the same number of moles of H2O, and therefore the enthalpy change for both the reactions is the exact same. All right. A butane burner is used to heat water. The MR of butane is 58. The enthalpy change of combustion of butane is negative 2,877 kilojoules per mole. 250 grams of water is heated from 12 degrees Celsius to 100 degrees Celsius. The burner transfers 47% of the heat released from the burning fuel to the water. Assume that butane undergoes complete combustion and none of the water evaporates. What is the minimum mass of butane that must be burnt? So here, right, we want to find the mass of butane that must be burnt. Okay, we want to find the mass of butane that must be burnt, right? In order for the temperature of the water to rise by 88 degrees Celsius, okay, assuming that only 47% of the heat would be transferred. So the first thing we're going to do is we're going to figure out the amount of energy that would be transferred to the water, right? So we know that Q is equal to MC delta T. Now over here, the mass of water is 250 grams. The specific heat capacity of water is 4.18 joules per gram per Kelvin. And the change in temperature, right, we're going from 12 degrees Celsius to 100. So that's 88 degrees Celsius, right, or 88 Kelvin. So what is the amount of heat energy that must be transferred to the water? This is equal to 91960 joules. Now we need to figure out how much butane must be burnt, but we first need to figure out how much energy we need to release in total in order to get this much energy transferred to the water. We know that only 47% of the heat released from the fuel is transferred to the water, right? So the total amount of energy that we need to release, right? The total amount of energy that we need to release is something we have to calculate, right? We know that the total amount of energy that we need to release, let's call that this, right? The energy subscript T, this is the total energy that we need to release. 47% of that total energy, 47% of that total energy, right, is going to be transferred to the water, right? So the energy transferred to the water would be 91960 joules, right? So we can figure out what the total amount of energy that we need to release will be. The total amount of energy that we need to release will be. So we know that the total amount of energy that we need to release would be 1.957 into 10 to the power of 5 joules, right? If this is the total amount of energy that was released, if this would be the total amount of energy that would be released, 47% of this energy would be transferred to the water, right? So this much energy would be transferred to the water, and hence the temperature of 250 grams of water would rise by 88 degrees Celsius. Now the question is, how much butane do we need? How much butane do we need to release this much energy? Now they've told us that the standard enthalpy change of combustion of butane is negative 2877 kilojoules per mole. That means that if I had 1 mole of butane, right, if I had 1 mole of butane, right, then the amount of energy that would be released is 2877 into 10 to the power of 3, right? So this is the amount of joules that would be released. This is the amount of joules that would be released if I was combusting 1 mole of butane. So the question is, how many moles of butane would I need to combust? How many moles of butane would I need to combust in order to get an energy of 1.957 into 10 to the power of 5, right? Is 195,700 joules. So then the number of moles of butane that we get is equal to a number of moles of butane that would need to be combusted, 0.06802 moles, right? Which means that the mass of butane will be the number of moles times the molar mass, which is equal to 0.06802 times the molar mass of butane, which is 58, right? So therefore, the mass of butane that we would need to combust is 3.94 grams, okay? So 3.94 grams of butane would need to be combusted, okay, in order for us to release this much energy, and 47% of that energy would be transferred to heat 250 grams of water by 88 degrees Celsius. So now we're going to move on to the next question. Okay, the next question that we're going to do is this one. Okay, this guy right here. Let's try to find that question. Okay, here it is. The enthalpy changes of two reactions are shown. What is the enthalpy change for the reaction shown? So over here, right, the reaction that they've shown is when potassium hydrogen carbonate is decomposed to form potassium carbonate, water, and carbon dioxide, right? And they've given us information about the neutralization of potassium carbonate and the neutralization of potassium hydrogen carbonate. So since we have information about their neutralization, right, we know that if potassium carbonate is neutralized, we get KCl, salt, carbon dioxide, and water. And if potassium hydrogen carbonate is neutralized, we get KCl, water, and carbon dioxide. So what's missing in this cycle is neutralization products, right? What we have here is neutralization, right? So we have neutralization products, salt, carbon dioxide, and water, right? We're neutralizing potassium carbonate, and we're neutralizing potassium hydrogen carbonate, okay? So we have neutralization missing, right? So we have neutralization products, right? Now, over here, we have 2 moles of potassium hydrogen carbonate. This enthalpy change value of positive 32.8 is for 1 mole being neutralized. So this would be 2 times 32.8, right? Positive 32.8. We have 1 mole of potassium carbonate, and the neutralization for that is negative 34, right? And then this enthalpy changes are unknown, right? So what we can say is, if we look at this cycle, all the arrows are pointing towards the neutralization products, and all the arrows are starting from the reactants. So we can say that we can decompose potassium hydrogen carbonate and then neutralize potassium carbonate, or we can directly neutralize potassium hydrogen carbonate, right? So we can say that x minus 34, right? We're going from here to here, either in 2 steps or in 1 step. So we can say x minus 34 is equal to 2 times 32.8. And that gives us x as positive 99.6 kilojoules per mole. All right. An energy cycle is drawn for the following reaction. Okay, this reaction here. The standard enthalpy of formation of BrF3 is negative 301 kilojoules per mole. The enthalpy change of BrF3 liquid to BrF3 gas is positive 44 kilojoules per mole. What is the average bond energy of the BrF bond in BrF3? So if we're starting with the elements, right, we're saying if we go directly from the elements to the gaseous atoms, the enthalpy change is positive 698 kilojoules per mole. Okay. Now the enthalpy change of formation is when we form 1 mole of BrF3 liquid from its constituent elements. Here we have 2 moles of BrF3. So this would be 2 times negative 301, since we're forming 2 moles of BrF3 liquid from its constituent elements, right? That will be 2 times the standard enthalpy change of formation, right? The enthalpy change of BrF3 liquid being converted to BrF3 gas is positive 44. Again, this is for 1 mole of BrF3 liquid to 1 mole of BrF3 gas. We have 2 moles of the liquid being converted to 2 moles of the gaseous products. So this will be 2 times positive 44, right? And we have to find the BrF bond energy. Okay, so let's say that the BrF bond energy is X. Okay, let's say that the BrF bond energy is X. That's what we have to find, right? Now, if we have gaseous covalent bonds here, right, we have 2 moles of BrF3, right? We have 2 moles of BrF3, which means that we have 6 moles of gaseous covalent bonds. We have 6 moles of gaseous covalent bonds, right? So when we go from the gaseous molecule to the gaseous atoms, here we're breaking 6 moles of the gaseous covalent bonds. So that'll be 6 times the bond energy. So this is 6x, right? So if you look at our energy cycle, all the arrows are going away from the elements and all the arrows are going towards the gaseous atoms. So we can say we can go from elements to gaseous atoms in a single step, or we can first convert the elements to the liquid BrF3, vaporize that, and then break the gaseous covalent bonds, right? So what we can say here is, 698 is equal to 2 times negative 301 plus 2 times 44 plus 6x, which gives us x as positive 202 kilojoules per mole. Okay, so that is the average BrF bond energy. So the answer over here is B. Over here, again, if we look at the energy cycle, right, think of this as a vector diagram. We're starting with the elements. That's where all the arrows are pointing away from, right? And we're going towards the gaseous atoms. We can go there directly. That's our resultant vector. That's 698. Or we can go there in 3 steps. By first forming BrF3 liquid from the elements. So over here, since we're forming 2 moles of BrF3, this would be 2 times the enthalpy change of formation of BrF3 liquid. Okay. Then they've told us the enthalpy of vaporization of BrF3 liquid to BrF3 gas. That's again for 1 mole of BrF3 liquid being vaporized. Right? Since we have 2 moles, that'll be 2 times positive 44. Okay. And then once we have gaseous covalent bonds, we're breaking those covalent bonds to form the gaseous atoms. We don't know the bond energy. That's X. Now, if we have 2 moles of BrF3, that means we have 6 moles of gaseous covalent bonds. So we're breaking 6 moles of gaseous covalent bonds, right? And the energy for that would be 6x, x being the bond energy of 1 mole of gaseous covalent bonds, right? That's the energy needed to break 1 mole of gaseous covalent bonds. Here we have 6 moles, so that'll be 6x. So we're saying we can go directly from the elements to the gaseous atoms, that's 698, or we can go indirectly, right? We can first convert to liquid, then to gas, and then to the gaseous atoms. That'll be 2 times negative 301 plus 2 times 44 plus 6x is equal to 698. We have the same starting point, same ending point. You can go in 1 step, or you can go in 3 steps. And using this relationship, we can calculate X, which is the average bond energy, as positive 202 kilojoules per mole.